Welcome back to the G&T seminar. So this week's speaker is Marvin Dippell from Cologne, and he's going to tell us about homotopies for differential Hochschild cohomology. Please.
Okay, first, thanks for having me here again. I'm really happy to be back in Prague, and thanks, Jakub, for the really nice pre-seminar talk. So essentially all the difficult stuff was already in his talk, so we will be really relaxed now for the next, well, I can be quick now that everything is essentially done. Well, anyway, so I want to present some results from a common project with Chiara Esposito, Jonas Schnitzer, and Stefan Waldmann, and I think all of them have been here in the last year, at least, so you know where to complain if I tell something stupid. Okay, so you can find the paper online on arXiv. You've also had it on Jakub's slides. And it's kind of a mixture, a little bit of differential geometry and algebra. I will try to keep the differential geometry low and be a little bit more specific on the algebraic part, which is also kind of the interesting part. So how is my talk divided? So I will start with a little bit of motivation on deformation quantization and the Hochschild-Rosenberg theorem. As far as I know, a few weeks ago, I guess for Jonas' talk, maybe Julius did actually a pre-seminar about deformation quantization. So I guess most of what I'm talking about in this part you have already heard a few weeks ago, but I guess it's still good to remember these things. Okay, second part will be essentially the proof that I want to show you of the HKR theorem, which consists of two main ingredients, the symbol calculus and a double complex of the form we have already seen in the pre-seminar. And then depending on how much time I have left in the end, I will talk a little bit about applications and where this kind of improved HKR theorem can actually be used to get some new results. So let's start with the general idea of deformation quantization. So quantization is when we want to kind of construct a quantum mechanical system out of a classical mechanical system in our case. And in deformation quantization, we start with the classical mechanical system modeled by a phase space. So we have a smooth manifold M in our case, together with a Poisson structure, Poisson bivector field pi. So the smooth manifold M is really the phase space of our classical mechanical system. So every point in this space kind of, you can think of it describes all possible positions and momenta of all particles involved in the system, for example. And then kind of the Poisson bivector field pi gives you the dynamics of the system. So it tells you how your system evolves over time. Now, to get in contact with quantum mechanics, we have the problem that in quantum mechanics, well, in the usual formulations, there's no phase space available. But in quantum mechanics, we describe things using non-commutative algebras of observables. So the first step is reformulating our Poisson manifold, our phase space, in terms of the algebra of observables on this Poisson manifold. So here C infinity M for me is just the algebra of real or complex valued smooth functions on the manifold. And then our Poisson structure, our Poisson bivector field pi, induces an algebraic Poisson structure on this commutative algebra here. So here we have a Poisson algebra in the algebraic sense. Okay, now in formal deformation quantization, what we try to do is we try to build out of this commutative algebra of observables a non-commutative one. And this non-commutative algebra is then interpreted as the algebra of observables of our quantized quantum system. Since I'm talking about formal deformation quantization, what we're looking at is formal power series in the algebra of observables on our smooth manifold. And what we're trying to achieve is trying to find such a non-commutative, what we call a star product on this algebra, turning it into a possibly non-commutative algebra. And the non-commutativity is really the quantum effects we have. Okay, so a little bit more precise, what is a star product for us? So a star product is a product on the formal power series on the algebra of functions. And it should be associative, but possibly non-commutative. And it should be related to the pointwise commutative product on the algebra of functions here as follows. So if we write down the star product in powers of our formal parameter h bar, so this is not a number here, it's really just a formal parameter, then we get these these operations CR here, where we can plug into functions and we get another one. And if we write down the star product of two functions in terms of the formal parameter h bar, then we want that in lowest order, we actually get the pointwise product from our classical mechanical system. So it's really the product of functions on the manifold N. Right? So in this sense, the star product should be a deformation of the pointwise product. So we get higher order terms here, which are introduce the non-commutativity, let's say. And since we are coming from differential geometry and we want to get in contact with this differential geometry and Poisson side, we want these operators CR here to be bidifferential operators. So they should be differential operators in each slot of maybe arbitrarily high degrees, but differential operators. Okay, so that's the connection of the star product to the algebra of functions, to our observables. And we also want that our star product is connected to the dynamics of our system, so to the Poisson bracket. And what we want is that if we look at the commutator with respect to this non-commutative star product, well, in lowest order, so in order 0, kind of we have a commutative product, so there it vanishes. But then in order 1 of h bar, we want to get back the Poisson bracket we started with. And then we get some higher order terms, right? So actually, you could also say, well, from the beginning, forget about the Poisson structure. We don't need that. We can always reconstruct a Poisson structure from the commutator of a given star product. So if we find a star product, it will always be, so a star product in the sense of it satisfies 1 and 2. It will always be a star product for some Poisson bracket, which we can actually reconstruct. So from now on, I will mostly not talk about the Poisson structures anymore because we can always reconstruct it. Okay, so that's the goal of finding star products and also understanding, well, are there star products? Do these actually exist? And how many different star products can we actually construct on a given Poisson manifold? And the classical tool to understand deformations of an algebraic, of an associative algebra, is given by the Hochschild complex. So, little algebraic reminder: from now on, A is just some associative algebra with multiplication mu, and we want to study deformations of this A in this sense. Wrong. Okay, here we are. In the sense that we want still to have an associative multiplication, which starts with the old multiplication in lowest order. Okay, and what we do to study this is we introduce the classical Hochschild complex. So the Hochschild complex consists in degree k of homomorphisms from the k-fold tensor product of A with outputs in A. So we have k slots and one output. And on this graded module, we can construct a differential, which I didn't write down here. But what you want to do is you take a homomorphism with k inputs. You want to construct something with k plus 1 inputs. So what you do is you take k plus 1 elements, you multiply two neighboring elements together, then you have just k elements left, and those you can plug into your cocycle from the complex here. Okay, so this gives you a complex, and even more, we have an additional structure. We can also define a product on this Hochschild complex, but just taking the tensor product of two cochains. Then the output of those are just functions, and these we can multiply, or well, they are not functions, they are elements in our algebra, and these we can multiply, right? And this gives us a new cochain in our complex. So together, we get a differential graded algebra on this Hochschild complex. Okay, why is that interesting for our study of star products? Well, because this Hochschild complex describes, it controls the deformation theory of our algebra. So if we look at the lowest orders, so order 0 and order 1 are really, really simple. In order 0, in general, we get the center of our algebra. In particular, when the algebra is actually commutative, so for example, the algebra of functions on our smooth manifold, then this is just the algebra itself. Right? In the first degree of the Hochschild cohomology, we get the outer derivations, so all derivations modulo the inner derivations, so those derivations which we get by taking commutators with a fixed element. And again, if our algebra A is actually commutative, for example, the algebra of smooth functions, there are no inner derivations. The commutator is always 0. So here in this case, we just get the derivations. Okay, now in order 2 and 3, it becomes a bit more interesting for deformation theory, because in order 2, as you can read here, you get equivalence classes of infinitesimal deformations. So what do I mean by infinitesimal deformations? Well, I mean kind of deformations where our product, the new product, which we call star product in this case, is not really associative, but only the associativity holds up to order 1 in H bar. But it might fail in higher orders. Okay, but these infinitesimal deformations are classified by the second Hochschild cohomology. And I told you it's just equivalence classes. Well, because you could say to star products that are, or to deformations of your algebra that are linked kind of by an automorphism of the algebra that keeps doesn't change the undeformed product. So in order 0, it's just the identity. Then you should consider these two deformations to be the same, right? And in the second Hochschild cohomology, you find the equivalence classes of those. So really different infinitesimal deformations. Okay, so if we know the second Hochschild cohomology, we already know something about the deformation theory. Problem is now, well, if we have an infinitesimal deformation, can we actually extend it? Can we, for example, extend it to a deformation where we have associativity up to order 2? And can we extend this one to a deformation up to order 3? Can we extend it in the end to a full formal deformation, which is really associative in all orders? And obstructions to this problem you can find in the third Hochschild cohomology. So especially when the third Hochschild cohomology is 0, there are no obstructions to the extension, so you can always extend your infinitesimal deformations to full deformations. In most cases, the third Hochschild cohomology will not be 0. There will be obstructions, but then you have to find other means of kind of proving that you can extend stuff. Nevertheless, the Hochschild cohomology is really important in deformation theory and used also in more deep, let's say, results in this field. Okay, so back to our case, we're not interested in any algebra, but just in the algebra of smooth functions on a smooth manifold. And as I told you, we are not interested in some deformation, but we are interested in deformations by bidifferential operators. These operators CR should be bidifferential operators. So we're actually not interested in the full Hochschild complex, but only in a subcomplex which consists of maps like those with k inputs, 1 output, which are differential operators in each input, so multi-differential operators. And you can easily check that the differential and the product, the cup product here, go down to the subcomplex. So from now on, we will not be looking at the full Hochschild complex, but just the subcomplex, the differential Hochschild complex. And these are just the multi-differential operators on our manifold. Okay, so the question would now be, well, do we know what this Hochschild cohomology looks like in this case? And yes, we actually do. And we know this for a long time already. So this statement is originally from algebraic geometry, but was later on reformulated in differential geometry by many people. Okay, let me formulate it like this. So we have a map from the multivector fields to the differential Hochschild complex. So multivector fields just wedges, antisymmetric algebra of the sections of the tangent bundle. And this we consider here with a differential 0. And on the other hand, we have our Hochschild, the differential Hochschild complex with the Hochschild differential I talked about. And this map is actually a quasi-isomorphism. So it gives us an isomorphism after going to cohomology. And since we have the 0 differential on the left-hand side here in cohomology, we just get the multivector fields. And on the right-hand side, we really get the differential Hochschild cohomology we're interested in for finding star products, for finding quantizations of our Poisson manifold. And this HKR map is really, really simple. So if we have as input here a multivector field, so each of this x1 to xk is just a section of the tangent bundle, then what we do, well, so this is supposed to be the Lie derivative of the vector field, but it's nothing but understanding the vector field as a derivation of our algebra. So we just view every vector field as a derivation, and then we use the cup product from before. So essentially, we just take the tensor product and then multiply in the end. And the rest here is just anti-symmetrization because we plug in something anti-symmetric. So it's a pretty simple map, which essentially just tells us, okay, interpret multi-vector fields every single factor as a derivation, and derivations are differential operators, so we end up in the differential Hochschild complex. Okay, so you could say, well, we are done. We know everything we need to know, but there are some problems to the proofs of this HKR theorem in the setting of differential geometry, I would argue. So most of the proofs that we know, at least, are of local nature. So they compute the cohomology by, well, taking your big manifold and then say, okay, well, let's just look in a local chart. In a local chart, we are in Rn. In Rn, we can compute by hand things, can compute the cohomology, and then we glue things back afterwards with a partition of unity. Well, this works. This gives us the cohomology. Problem is if we have a manifold or a classical mechanical system that has a bit more structure. For example, if we have a symmetry on our system, so we have a Lie group action, for example, the algebra action, then, well, if you go to the local patch and want to, to the local patch and want to glue it together afterwards, you get problems when it comes to the equivariance of your maps, right? If you bump things down, it will not be equivariant, at least if you don't have an invariant partition of unity, which in general you don't. So if you want to search for invariant star products, then this doesn't really compute. Well, these proofs don't really work here in this more structured situation. Moreover, it's often really a good thing, let's say, not just to know only the cohomology itself, but to have means to construct potentials of exact things. So in other words, to have a homotopy that really tells you how much does my Hochschild co-cycle actually fail to be exact, and in which way does it do it. So the goal of my talk will now be to construct a deformation retract of this form, so where we have the classical HKR map I just showed you before, but now we want to find a quasi-inverse on the level of the complexes together with a homotopy that really induces this isomorphism on cohomology. Okay, and here you see already where we're going. Here we will need some techniques from Jakub's talk before. Okay, so let's start with the improved HKR theorem. So and we begin a little bit with a general strategy. So remember, that's the classical HKR map that we have, and we want to find a quasi-inverse. So first thing is, well, the differential Hochschild complex, that's nothing but the multi-differential operators. That was kind of our definition. And the first step, we want to identify this differential Hochschild complex, these differential operators, with another complex which we call the coalgebra complex. Okay, we will see in a minute what this actually is. And this is really an isomorphism of complexes. Okay, and the nice thing here is we can somehow hide all of our geometry inside this isomorphism. Even though the kind of differential operators are, you could argue, really a geometric object, on the other hand, this coalgebra complex, this is really just an algebraic thing. So instead of trying to compute the differential Hochschild cohomology in this sense, we use this isomorphism and try to compute it in this algebraic setting. So here we hide all of our geometry. And then on the left-hand side, well, we first just give the multi-vector fields a new name. We call it the Chevalier-Allenberg complex because you can interpret it in this way. And then we want to connect this coalgebra complex and this Chevalier-Allenberg complex by a double complex, which we call the Van S double complex. And here you see now these maps go both into the, well, they go in different directions, right? But thing is, these are not isomorphisms anymore, but just quasi-isomorphisms. Actually, they will be really given by deformation retracts. And then you see already a little bit where we are in this setting of having two complexes and a double complex in the middle and deformation retracts from the sides. And the second part is completely algebraic. So there's really, this is really, I would say, kind of the easy but more interesting part of this.
Just a quick question, Marvin.
Sure.
So you said for the multi-vector fields, you took the differential equal to 0, right? And now you're saying this is the same thing as Chevalier-Eilenberg, but of course there it's probably you're talking about the dual where your bracket now corresponds to the differential, right?
Well, yes. I mean, so we're talking kind of about let's say abelian Lie algebras or abelian Lie co-algebra. So our bracket is kind of 0, meaning that on the Chevalier-Eilenberg complex our differential is 0. So it's a really stupid object in this sense, but. Yeah, I can tell you more why we call this a Chevalier-Eilenberg complex maybe later when we see these objects. Sure. Yes. We will need to construct that kind of in the similar way we have seen before. Okay, so let's get kind of the geometry out of our way. So we need one more ingredient for this identification of our differential operators with this coalgebra complex, and that's a covariant derivative. So essentially, covariant derivative lets us compute higher order derivations on a generic manifold. And out of a given covariant derivative, we can always construct what is often called a symmetrized covariant derivative, so an object like that. I don't want to go into details. I just want to tell you, well, there is a statement really classical. So the first thing where we could find it was lecture notes from Palais from 65. So this is some classical stuff from differential geometry, which tells us that we can identify differential operators or multi-differential operators with many slots, which are nothing but our differential complex, differential Hochschild complex. We can identify those with the tensor algebra of the symmetric algebra of the modular vector fields. Okay, so how do we do that? So I wrote you down the definition of the map just to get a little bit of feeling. So this op means we want to construct a differential operator out of this tensor product of x1 to xk, and each x is from the symmetric algebra of the vector fields. Okay, we have to apply it to k functions, and this should be a differential operator. So we ignore the prefactors and just look at the first factor here. So what we do is we apply our symmetrized covariant derivative as many times to the function as we have symmetric degree in our x here, which essentially just means, okay, we collect all possible partial derivatives of f. And then we get an object in here. So we have symmetric powers of the sections of the cotangent bundle. So we can insert the x1 in this case and just get a function back. And this insertion of the x's just means, okay, here we have collected all possible partial derivatives, and now we'll just apply those partial derivatives which we have kind of encoded in this x here, right? So the symmetric algebra here is just Schwarz lemma telling us that partial derivatives commute, and every kind of single partial derivative is one of the vector fields in here. Okay, so just to get a little bit the feeling why this should be true. So the question is now, well, we have an identification of differential or multi-differential operators with this tensor algebra of the symmetric algebra, but on the right-hand side we have a differential, and we want to compute the cohomology. So what's the differential on the left-hand side? Okay, for this, we now come to something that you probably all know very well. So for a second now, or let's say for a little bit, we replace our module of vector fields now by just some module V over some algebra A. Yeah, you can think of vector fields and functions, but it's enough for us to have some module, some A module. Okay, what we can do is we can construct this symmetric algebra, and it is actually a co-unital co-algebra, right? And as co-product, we just use the shuffle co-product. So the V's here are my symmetric product. And what we do is we just split this list of x1 to xk in half at all possible points, and then we symmetrize on the left and on the right. Classical thing. But it's not only a coalgebra, we also have a co-unit, and the co-unit is just given by projecting to symmetric degree 0, or projecting to the algebra itself, right? Okay, and for this co-unit co-algebra as V, we can actually write down what's the reduced co-multiplication by just removing the boundary terms in the sum here, so where all of the x's are on one side or on the other side. Okay, why do I tell you that? Well, because now on the tensor algebra of the symmetric algebra, we get a differential by just extending this reduced shuffle coproduct as a graded derivation to the tensor algebra. Okay? And this is what we call the coalgebra complex. Not a standard name. Some people call it Hochschild cohomology. I've also seen Cartier cohomology for this guy, or I mean, there are different names, but for us, it was just important to say, okay, that's just a coalgebraic thing that we construct out of V. Right?
Just a quick question, Marvin. So here, the 0 degree of the symmetric algebra, is this the ground field or is it the algebra?
It's the...
Because you project to the algebra, so I was guessing that, okay, you build this over the algebra?
Yes.
Then so also the tensor product should also be over A, I guess, in this case.
No, it should not. Wait. I mean, no, the tensor product should not be over A. This should be over the field. Okay, now I'm confused. Or should it? I don't know.
Because I guess you want to build like an R or a C coalgebra and not so.
Yeah.
Not
No. You're right. Yeah. So it should be the field. Yeah. Okay. Sorry. Yeah.
Then probably the co-unit here is
okay.
Maybe this is just 0, so that this is a non-co-unital coalgebra.
No, it should be still the projection onto degree 0 of your symmetric algebra.
Okay, so you take the 0 degree to be the algebra, but you view this as a K coalgebra. So.
Yeah.
Okay. But then epsilon, yeah, this is not a map to the field, right?
No, yeah. This is what I did wrong. Yeah, okay. Well, it should be the degree 0 should be the field. Yeah, and this should be the projection onto the degree 0 of the symmetric algebra.
Okay.
Yeah,
this makes sense. Huh?
Yeah, not the A here. Okay, so that's the differential we build on this tensor algebra of the symmetric algebra. And now in our case where we're interested in the module being the vector fields on our manifold, well, under this isomorphism of the symbol calculus, it turns out this is exactly the differential you get when you transport back the Hochschild differential from the differential Hochschild complex. So instead of computing the Hochschild cohomology with this Hochschild differential, we're just interested in this kind of coalgebraic cohomology with respect to this, let's say, easy differential, which is just a reduced shuffle coproduct extended to the tensor algebra. Okay, so in this sense, we hide now all our geometry in this isomorphism and now only are interested in computing this coalgebra cohomology and getting homotopies for that, actually. Okay, so we have fixed the right-hand side, and now we try to find this double complex that actually connects these two here. Yep.
It seemed that for the isomorphism, you need a choice of a connection, right?
Right.
But this does not appear in this differential here.
Right.
So it's just you prove that it's independent.
Yes. Yeah. So it's always this differential, but you're right, this isomorphism itself depends on the choice of covariant derivative. So we will see this later on that at some points the choice doesn't matter, at some points it changes a little bit our constructions. Okay, so let's go now to the construction of this double complex here. So as before, as we've seen in Jakob's talk, so we're considering the following double complex. So it's sits in the upper right corner of our plane. So it starts in 0, 0 and goes up in both directions. And it's the fun S double complex constructed like this. So we have 3 tensor factors. So one is the tensor algebra of the symmetric algebra, so the object we had before. Then the second tensor factor is the symmetric algebra again. And the last one is the anti-symmetric algebra, the wedge product of V, right? And this you already see here. If we think of V as the vector fields, then this is what we want to have in the end. Okay, now let's introduce some differentials on this double complex. So first, the horizontal differential should go up here by 1, and it should increase the wedge degree by 1. So what do we do if we plug in an element like this? So X is from the tensor algebra, phi symmetric algebra, psi antisymmetric algebra. We do nothing on the tensor algebra. We use the shuffle coproduct on the symmetric algebra, and we move the right-hand leg from the shuffle coproduct, so that's Wheeler notation here, just to the right-hand side, project to degree 1 in the symmetric algebra, and then we can just take the wedge product and get another degree in the symmetric part here. So that raises the degree, the horizontal degree by 1, and that's a differential.
We write 0 and 1 as usually the coproduct is like 1 and 2.
Yes, because we think of SV more as a co-module, and we will also sometimes need the left coaction and sometimes right coaction. Then we have -1 and 0, and that's where we, I don't know. We've not really found a consistent way, so we just stuck to the 0, 1 thing. Okay, and then as we have seen in Jakobstorff also, we can actually, in every fixed row, we can find the cohomology of this complex. And it is just the degree 0 back here. So it's just the degree 0 of SV and degree 0 of wedge V. So it is just the tensor algebra of the symmetric algebra with fixed tensor degree in every row, right? So in yes, so, and we get projections and inclusions. So for example, here we can include this TSV part by simply using 1 and 1 in the SV and in the wedge V part, so in degree 0. And we can project down by simply projecting SV and wedge V to the degree 0. And then we can also write down a homotopy that actually shows that this is the cohomology of this row. And the homotopy is also pretty easy. So again, we have some prefactors, we don't care, we do nothing on the TSV part. And what we do now is, well, we use kind of the shuffle coproduct now on the antisymmetric algebra. And we just move one leg, and here I use the -1 because we use the left leg, move it to the symmetric algebra and take the symmetric product. So here we reduce the antisymmetric degree of wedge V by 1. And then you can show, okay, this is really a deformation retract in every row. Okay, now on the columns, we can do something really similar. So we want to increase now the tensor degree by 1. So how can we do that if we apply it to x, phi, xi? Well, one way is applying our delta from before to x. So this was the reduced shuffle coproduct, which we apply to every single x, and then it splits into 2 parts. So it increases the number of the tensor degree here by 1. Another possibility would be that we use the shuffle coproduct on the symmetric algebra in the middle and move one of the legs as a new tensor slot in this TSV part here. Right? This way we also increase the tensor degree by 1. Here we have the projection onto the positive parts for some reason. Okay, and then as before, you can show that the cohomology in each column is exactly given by wedges of V. And again, the inclusion is really simple. It's just included in the wedge V part and use the degree 0 once in the tensor algebra and in the symmetric algebra. And projecting down just means, okay, project to tensor degree 0 and symmetric degree 0. And then again, we can write down an explicit homotopy, which is again pretty simple. So we do, this time we do nothing on the xi. we project the symmetric part, the middle part, the phi here, to degree 0. And then we just move the rightmost tensor leg as a kind of out of the tensor algebra and view it as the new middle part here. So this reduces the tensor degree by 1, and you can just compute that this is actually a homotopy for this differential, and it gives you this guy, this what we call the Chevalier-Eilenberg complex here as the cohomology in every single column. Okay, you should note here and also in the rows, well, here we get the coalgebra complex, but without the differential. So at the moment we have differential 0 on both sides. Okay, so that's our big picture. So we have our double complex in the middle, and the columns and rows are related to these two complexes. But these two complexes are really just related to the rows or columns, not yet related to the total cohomology, to the total complex. And to do this, well, to relate it to the complex with differential being just the sum of the horizontal and the vertical ones, we do exactly what Jakub showed us before. So again, that's our little picture. We have deformation retract on each row. We have a deformation retract on each column with homotopies here. Can I move that? With homotopies here for the columns and for the rows. Now we want to relate them really to the full total complex. And we do this by using the perturbation lemma. So we view first delta as a perturbation of partial. So you need to check that it really is a small, and in this case actually locally nilpotent perturbation. Then you apply the perturbation lemma, and what you get is, well, you have to perturb your homotopy. So instead of a small k, I have a capital K here. You have to perturb your inclusions and projections, J and Q. In this case, actually, the inclusion just stays the same. It stays unperturbed, but Q gets perturbed. And then before we had our 0 differential here, actually. But now we also need to perturb this differential, and we get a new differential on the coalgebra complex. And because, well, we chose our differentials on the Van S double complex in the correct way, this differential is really the coalgebra complex, the Hochschild differential we want to have here. So that's really the complex that computes our Hochschild cohomology. Okay, so this tells us already in the rows now that the cohomology of the coalgebra complex is the same as that of the total complex of this double complex, and we have a deformation retract. And now we do the same on the columns. We now view partial as a perturbation of delta. So we perturb, we get a perturbed homotopy here. Again, the inclusion I stays unperturbed, and we get a perturbation of the projection downstairs. And we started with a 0 differential, and it turns out, and that's really useful here, that actually the 0 differential after perturbation stays 0. Which is a really nice thing, because now, well, we know the cohomology of this guy is the cohomology of this guy is the cohomology of this guy, but here the cohomology is just the complex itself. Okay, now putting these two things together, we can directly relate the coalgebra complex and the Chevalier-Eilenberg complex. And that's exactly what Jakub also showed us. That's just a composition of deformation retracts. So we get a new deformation retract directly between Chevalier-Eilenberg and coalgebra complex. And we call these the Van Est maps. So these are just the compositions of, well, I and Q, or of J and then P. And the homotopy we get is just a combination of the perturbed maps we have in here. Okay, so now we're essentially done, right? Because, sorry, I first wanted to recall a little bit the formulas, let's say. So you've seen these formulas in Jakub's talk. So just want to show you the perturbed maps are really, really easy. I mean, it doesn't look like that at the moment, maybe, but remember this delta here, this was just the shuffle coproduct, right? It was just shuffling things up. The K here, that was just moving one symmetric thing to the tensor algebra. This H was just moving one antisymmetric factor to the symmetric one, and the delta was just moving a symmetric one to the antisymmetric one. So all these maps are actually really, really explicit, and they are just built out of really simple coalgebraic things, right? Even though this looks complicated at first glance, you can really work with those, especially in low orders. You can really write it down by hand. And for example, if you want to write down what these Van Est maps between the coalgebra complex and the Chevalier-Allenberg complex are, you can actually do that. So the Van Est map here, which goes from coalgebra, so the TSV, to the wedges, well, it does nothing but projecting every symmetric algebra X here to degree 1 and then wedge it together. Right? So it just projects to degree 1, that's it. And on the other hand, going the other direction, the Van Est -1 goes from Chevalier-Allenberg to coalgebra. It just includes the factors of the wedge of V as degree 1 elements in every tensor slot and then anti-symmetrizes. That's it. When you apply to one element, yeah, then it's finite at some point. That's the local nilpotency we had before. So it kind of as maps, you have this infinite sum, but if you apply to elements, it's just always a finite sum. So it's well defined. Okay, so we can combine this now in our special situation where we have our module V being the sections of the tangent bundles or the vector fields. We combine this Van Est double complex with our symbol calculus with this isomorphism from before. And what we get is really the HKR theorem, but this time with a homotopy that is immediately globally defined. Right? So we get now really the classical maps from the multi-vector fields to the differential Hochschild cohomology, which is just Van Est to the -1, the easy map I showed you before, and then we have to use our symbol calculus here. And as Thomas mentioned before, well, the Van Est maps are independent of the choice of our covariant derivative. That was just algebra. Inside this op here, there is the choice of a covariant derivative, but it turns out that if you apply it just to images of the Van Est inverse map, this is actually independent of the choice of the covariant derivative, and this is really just the classical HKR map I showed you in the beginning. But for the quasi-inverse HKR to the -1, here we first use the isomorphism from the symbol calculus and then the Van Est map. Here, this really depends on the choice of a covariant derivative. And also the homotopy we get, which is essentially just the homotopy from the Van Est double complex, and then identified with the symbol calculus, this also depends on the choice of a covariant derivative. Nevertheless, any such covariant derivative yields a deformation we tracked in this sense. Okay, questions so far? Because that's kind of the big statement. So now I would go to the applications and see how much time is left. Okay. So let's see how we can apply this kind of improved HKR theorem now to some specific examples, well, more or less specific examples. So first example would be if we start with a manifold and it has some additional properties, well, not properties, some additional information, some additional structure, namely that of a submanifold C. So we choose a submanifold C, and we would like to quantize it. We would like to find star products that are compatible with a submanifold. So they should be tangent in a certain sense. So what you can do now is you choose a covariant derivative that is adapted to the submanifold. This you can always find. And then you can see that the symbol calculus gives you an isomorphism between the differential Hochschild complex that is tangent or consists of differential operators tangent to the submanifold. And the symbol calculus gives you an isomorphism to the tensor algebra of the symmetric algebra, now of a slightly different module, namely the module of tangent, well, vector fields tangent to the submanifold C. Right? Okay, and this Hochschild complex here, this is what controls the quantization that takes into account the submanifold. So we would like to compute the cohomology of this guy. But with our technology from before, we can directly do that. We just replace V now, not by all vector fields, but just the tangent vector fields, and we immediately get a tangential HKR theorem. Okay, and this can help us now to understand how we can quantize Poisson manifolds with submanifolds. Okay, another example I told you already about. This was also one of our motivations why we looked at this. So if we have on a classical mechanical system a symmetry, so a Lie group or Lie algebra acting, and assume we have a invariant covariant derivative. You cannot always find this, but there are many, many cases where you can find these invariant covariant derivatives. And then the symbol calculus gives us an isomorphism between the invariant differential operators and the invariant elements in this tensor algebra of the symmetric algebra, in this coalgebra complex. Okay? So now we would like to use our technology from before to compute the cohomology here, but we cannot simply replace V now by another module, right? But, well, maybe quickly go back to this funny picture. If you vaguely remember the constructions of our deltas, of our homotopies, of the K, of the J, of the Q, whatever, all these constructions were actually functorial, right? So if we have a map from V to another module W, then we get maps between all double complexes and their corresponding deformation retracts here, right? So in particular, if we go to our example here, where we have a group acting by automorphisms, right? Then we immediately see that all these maps are actually equivariant. So they commute with the action of the group or the Lie algebra. And if all of these maps and objects are equivariant, we can actually restrict them to the invariant elements and immediately get a Van S double complex for the invariant coalgebra complex here. And then we just compose it with a symbol calculus and get deformation retracts for these invariant differential operators. And these are really the complexes that you need to study when you want to look at quantizations of systems with symmetry, right? Then you get invariant or equivariant star products. That's what is described here. And this is actually something new that came out of this, because the cohomology of the invariant differential Hochschild complex was only known, as far as we knew, for actions of compact Lie groups, or maybe, no, I think also for proper actions. But this was achieved by there was some, let's say, geometry really involved of the proper action, right? But there are simple actions which are not proper, but still allow for invariant covariant derivatives, and then you still get this statement. And again, all of this is global directly, and we have quasi-inverses. Okay, maybe another example in a slightly different direction. So we could also look at deformation quantization, not of general Poisson structures on general manifolds, but maybe you're interested just in simple cases, for example, linear Poisson structures on vector bundles. So if we assume our manifold itself is actually a vector bundle, and then you can talk about linear Poisson structures. Okay, for linear Poisson structures, it actually turns out where the phase space is actually the dual of a Lie algebroid. Okay, so as I said, we started with the linear Poisson structure, then the phase space is the dual of a Lie algebroid. And what we're interested in is finding star products that are, in a certain sense, homogeneous, that are compatible with this linear structure of our space. Okay, so what happened? Here we are. Okay, so what do I mean by a homogeneous star product? Well, on every vector bundle, you can write down what is often called the Euler vector field, so essentially a vector field pointing into the direction of the fibers of our vector bundle. And with this vector field, you can somehow count how many times does your differential operator differentiate in the direction of the fibers of your vector bundles. And that's this degree k here. And then we would call a star product homogeneous. Well, if these bidifferential operators CR, we always have, are always of homogeneous degree minus R. So they differentiate at most R times into the direction of our bundle. Okay, why is that interesting? Because Well, with the technologies I've told you before, because of the functoriality and the kind of equivariance properties, you immediately get a deformation retract, also in this case of having linear ortho structures on the dual vectors on Lie algebra. Okay, so that's just the statement now in this special situation as we had it before. But in this special case, this actually allowed us to prove more, because by simply counting some degrees, and the help of this deformation retract, this was really crucial for this statement. We were actually able to prove that in the special case of you wanting to deform Lie algebroids, you can really classify all possible homogeneous star products. And what we were able to show is that the set of equivalence classes of homogeneous star products is actually isomorphic to the second to the second Lie algebra cohomology, the Lie algebroid cohomology. Sorry. Okay, and I don't have time to talk in detail about this, but suffice it to say that we really needed this deformation retract a lot to accomplish that. Okay, maybe some more nice features. So you could also be interested not just in the Hochschild cohomology of some algebra, or in our case of the algebra of smooth functions, but you could also be interested in the Hochschild cohomology with values in some module over the algebra. And then you can still apply our techniques by applying the perturbation lemma once more. So if you have a module M where you want to compute the cohomologies in, then you can from this construct another perturbation of the total differential, which we call here B, and then apply the perturbation lemma again in both directions. And you get again a new fun S deformation retract, but this time for cohomologies or for complexes with values in a module. Okay, just the homology perturbation lemma again. So why is that interesting? Because if you want to talk about quantizations of surjective submersions, for example, you need exactly that. So if you start with a surjective submersion, you so think about a fiber bundle, and you have a covariant derivative that is adapted to this surjective submersion. And okay, we choose a horizontal bundle. You can always do that. Then the symbol calculus gives us an identification of the differential Hochschild complex with values in the differential operators on P, on the big manifold, with this guy. So you can interpret this as the co-algebra complex with values in the symmetric algebra of the vector fields on P. And then just this kind of extended finessed double complex with coefficients gives you, again, an adapted HKR theorem with homotopies that computes the differential Hochschild cohomology with values in the differential operator and gives you the vertical differential operators. Okay, this has been used to study the deformation of surjective submersions. And this brings us to my last example. So combining things from before, if you have a principal bundle, so you have a surjective submersion and a Lie group action, and you have a covariant derivative on M and a principal connection on P, kind of being compatible with a principal bundle structure, then you can combine these HKR theorems for surjective submersions and for Lie group actions and actually get an adapted HKR theorem that controls the deformation theory of principal bundles. And this really computes the cohomology of the differential operators on M with values in the differential operators on P that are invariant and gives you the invariant differential operators that are actually vertical. And this complex has been used to study formal deformation quantization of principal bundles. And we really can compute the cohomology here and get explicit global homotopies. Okay, that was my little collection of applications. And with this, I'm finishing. Thanks.
Maybe I can start with one.
Sure.
So for this last example here, so what do you mean exactly by deformation of a principal bundle? Like we deform everything? Or
Let's say I don't know.
okay.
No, Martin Bordemann and give me a name. You studied with him. Okay, let's say.
Let's maybe.
Huh? No, from Würzburg. No.
In,
Who did his PhD with Martin Bordemann?
Benedict.
Yes,
Hulle,
Benedict. That's that. Yeah, Benedict Hulle. He studied deformation quantization of principal bundle in this setting. So I'm not completely familiar in which, I mean, what is really his definition of a deformation of a principal bundle, but he used this differential Hochschild complex that we computed here.
Okay, so you cannot comment like what's exactly what you deform. Okay, I mean, and I don't quiz you.
No, sorry.
But yeah.
For us, it was just, okay, that's another case, another nice example where we compute things now really easily. Yeah.
Okay, more questions?
Maybe I should answer one of your questions during the talk, because I told you I will talk about it and I did not do it. Just regarding the names of our objects. So we called okay, so we called this the coalgebra complex because simply there was no name we could really fix. We called this the Chevalier-Eilenberg complex because the idea of constructing this double complex actually came from essentially work from Van Est from the 60s, I guess. And he showed that the group cohomology of a Lie group is actually the same as its Lie algebra cohomology. And he also constructed a double complex and showed via this double complex that everything is the same. But he did it kind of not in this algebraic way, but in a really geometric version, kind of in a dual version. And he also didn't use the deformation complexes, this deformation retracts, sorry. This was done later, I think, I don't know, 6 or 7 years ago by Meinrenken and Salazar. They wanted to extend this Van Est this Van Est theorem connecting Lie group and Lie algebra cohomology to Lie groupoid and Lie algebroid cohomology. And they used actually these deformation retracts, but still kind of in a geometric way. So what we did was kind of somehow just transporting this geometric idea into the algebraic world. That's why we still call this double complex the Van Est double complex, but because he essentially introduced that. And this is also why we call this guy the Chevalier-Eilenberg complex, because in some sense you can interpret it as the Lie algebroid complex of the Lie algebra that is the of the Lie algebroid complex of the Lie algebroid that is the Lie algebroid of the Lie groupoid, which is just a tangent bundle with kind of trivial so abelian groupoid multiplication, just a plus. So in some sense you can interpret these guys here as being some sort of groupoids and these guys as being some sort of algebroids or their cohomologies. So that's why we have the Chevalier-Eilenberg name here.
Does this mean, so you're saying that this Van Est double complex also kind of makes sense for more general groupoids then, or?
I think so, yes. So it's kind of a more special situation we have here. So we're not looking at pure groupoids, but kind of VB groupoids, so where all the groupoids are actually also vector bundles. And then there is a paper that computes cohomology of VB groupoids already, but he also doesn't get the homotopies. So I think you're right. We should be able to do this maybe for more general VB groupoids, but yeah, we didn't go into this direction.
Maybe a last question from my side. So All of this is very algebraic. Do you think you can also, maybe try to prove some results that are very far from smooth manifolds, but maybe some algebras, maybe even Hopf algebras or something in this direction?
I mean, I would be happy to know. So we still have some problems in interpreting what we actually did here. I mean, we came from geometry and realized this double complex and turned it into an algebraic double complex. But I think there should be a better algebraic interpretation of this funny double complex than saying, okay, well, it comes from geometry somewhere. So one way to see that, I think, is that this tensor algebra of the symmetric algebra is actually the cobar complex of the symmetric coalgebra. And in some sense, the wedges of V should be something like the co-Seul dual coalgebra connected to the SV here. So I guess there is kind of a more general interpretation in terms of co-Seul duality of operads. You know, we talked about this already a few times. And I would hope that one can kind of extend this construction for more general coalgebras and their co-Seul duals. But at the moment, I'm not 100% sure, to be honest. I mean, the computation just of the algebraic homologies, this has been known for a long time. I think Cartier himself kind of computed the cohomology of this complex at some point, but he did not get a homotopy and a quasi-inverse. So that's maybe the algebraic new thing here. So we just combine pretty simple algebraic tools, but I think these homotopies, as far as I know, are not known before. So.
Last chance for questions. Maybe also from the online audience. If you have a question, just go for it.
Maybe it's not really a question, but more like a observation slash remark. So to me, this von Est complex looks a lot like the Coso complex. If you look at quadratic algebras and their duals, only that you have this additional part which is given by the tensor algebra of the symmetric algebra.
Right, so that's what I meant when I quickly talked about co-Seul duals and stuff. So yes, so if you view this kind of in this quadratic algebra language, then this would just be the cobar complex of your symmetric coalgebra, and then this becomes just the co-Seul complex in this language. But okay, as I said before, I don't know if this construction works kind of for more general algebras or coalgebras than just the symmetric coalgebra.
It would be interesting to see.
Yeah.
Because also if I think about differential calculi, then sort of see that you have a quadratic duality. So at least for the reducible quantum Fleck manifolds, you can describe the maximum prolongation of a first order calculus as a by a quadratic algebra. And on the co-differential side, it's a quadratic coalgebra, and they are actually dual. I don't know yet if they have causality also, but maybe there's some implication of that. I don't know.
Okay, yeah, I didn't know that. Yeah. Then we should talk about this maybe.
Okay, great. So let's thank Marvin for a great talk. Thank you. And see you next week. Or actually not, in 2 weeks.
Oh.